Good afternoon and welcome to today's lecture in fluid mechanics. Today is kind of a special lecture. You know that we were planning on having an excursion to ETH to go and see the wind tunnel and to look at a few experiments. But obviously this is not possible in the current situation. I tried to develop a lecture, an online lecture like we have now, to show you some results or not results, some methods which are relevant for experimental fluid mechanics. Let me switch to the slide. I hope you have received the slides. I was a bit late in preparing them, but they should be online now. Obviously this is our schedule where we are. Just a little note, I will say something toward the end of the lecture again. Next week, we will have a tutorial on computational fluid dynamics. So what we do today on experiments, we'll do next week on computational fluid dynamics. And it will be more like an interactive workshop type of thing. But for today, we specifically look at the running experiments. And before we start with the actual methods and the facilities and let's say the rules behind experimental fluid mechanics, I just want to quickly review what the challenges are, the special challenges that we are facing in experimental fluid mechanics. Because what we want to do in every experiment, and that is probably true for any kind of physical experiment that you want to do, is you actually want to model reality. And you want to model reality in the sense that you can bring the system that you want to study in a certain configuration, a controlled configuration, and you want to bring it in a form that you can study it either in situ, where the phenomenon is happening, or, excuse me, or in the lab. And as soon as you want to go into the lab, and in experimental fluid mechanics, the lab might mean going into a wind tunnel, you usually have a size problem, right? You need to, in some cases, make the objects that you want to study smaller so they fit into your lab. So if you want to study the fluid mechanics of a commercial airliner, you have the problem that you can usually not put a full-size commercial airliner into your lab or into your wind tunnel. But it also goes the other way. If you want to study the microcirculation, usually you cannot see it. You can only see it under the microscope. So can you either devise something which allows you to study the flow phenomenon under the microscope, or can you increase, upscale the experiment such that the blood vessels you want to study are larger? If you make them larger, what things do we have to consider? Are the physics still the same if we change the size? These are questions we need to answer. Very similar, almost the same story are the dynamical scales. We have looked at turbulence, and turbulence is, at least on the smallest length scales, can be a very fast process. The turnover time of a small vortex at Kolmogorov length scale can be quite short. Combustion processes, if you want to study the combustion chamber of a, let's say, a gas turbine, of a jet engine, these processes can be very fast. So you somehow need to make sure you can understand these scales, maybe adapt them to your measurement technology. Boundary conditions, another problem. Usually boundary conditions is something you have to deal with, or you think you have to deal with only in computational fluid dynamics. That's not true. You also have to deal with boundary conditions in experimental fluid mechanics. You have to control the inflow and the outflow conditions. So in our lab, we, for instance, study heart valves. And of course, we can model the flow conditions around the heart valve, but it's difficult to actually model the correct inflow. How do we know what the outflow of the heart, which is the inflow to the heart valve, what it looks like? Unless we model the whole heart itself, which is by itself a complex task, we cannot realistically reproduce the inflow conditions to the heart valve. Same goes for the outflow. Unless we model all the blood vessels that come after the heart valve, something we usually don't want to do, we need to do something about representing the effect of whatever comes downstream. We need to make sure we have the right walls. This is not just true for biomedical flows. It's also true if you study, for instance, let's say a geophysical flow at large scale, atmospheric conditions. So usually you want to study something quite local, right? Say you want to study the wind going around a building, for instance. And you say, well, far away from the building, there's just atmosphere. Well, this might be true in reality, but in your lab, at one point, there will be a wall. So how far away do the walls of your lab or of your wind tunnel need to be such that we can consider them to be far away enough not to affect the problem? So it is the problem of boundary conditions. And then again, there's the problem of accessibility, especially a problem in all biomedical applications. Most biomedical flows are internal flows, internal in the sense they're inside the body, where we usually don't have access, and then we come into measurement technology. Usually when we want to go measure something, we need to, let's say, see it in a certain sense. In fluid mechanics, there are a lot of optical measurement methods, very nice measurement methods, but of course they need optical access to the flow system. And then finally, we come to the problem of actual measurement. And usually we want to measure pressure, which is, let's say, a bit more straightforward, and we want to measure velocity. That's what we usually want to find out. And velocity measurement is a real tricky task. And we need to make sure that the devices that we're using for measuring velocity are not so intrusive to the flow that they modify it, right? If you come in with a large device to measure your flow velocity, and that device is even larger than the object you want to study, you might just disturb the whole flow in the sense that your measurement is nonsense at you. Then we will see later on that many measurement devices are just point-wise measurement devices. So we can measure at one point in space, which is okay if you're only interested in one velocity, but in many cases, you want to have a global understanding of the flow field. So either you take your point-wise device and scan through the whole flow field, which takes time, and it also gives some limitations. You can only study steady flows, or you have a global method which measures a whole field, 2D or maybe even 3D, in one instant. Then, of course, accuracy is an issue, and resolution, and the obvious things of measurement technology. So these are probably not exhaustive. This is probably just a list, a few examples of special challenges of flows, of experimental fluid mechanics. Let us start maybe with the first 2 points, size and dynamical scales. There's an important thing we need to understand, and well, probably we have understood by now, but I would like to point out what it means in terms of experimental fluid mechanics. It's the issue of similitude, or let's just say similarity, dynamical similarity, how to scale an experimental model. Well, one part of similitude is the geometrical similarity, and I think that's the obvious part. If you want to scale, let's take the commercial airliner, if you want to downscale it such that it fits into your lab, obviously you should maintain the important features, right? Your scaled airplane should still have the wings at the same place, it should have a fuselage and tail fin and so on. You should also maintain, let's say, the geometry in terms of angles, aspect ratios. So at the end, it should just be a upscaled or downscaled representation of your airplane. I think that's clear and straightforward. The second similarity, dynamical similarity, is maybe a bit less clear what it means. We have learned, I think it was in the second lecture where we looked, or first lecture even, when we looked at the Buckingham pi theorem, that we can reduce most fluid mechanical systems to a set of dimensionless numbers. And we found that one of the most, or maybe the most important dimensionless number was the Reynolds number. And we saw that as long as we keep the Reynolds number constant, the rest of the physics, or let's say the flow field, remains the same. That's the only parameter that we can vary. So we should ask in our experiment to scale not just the geometry, but also all the other physical parameters in a way that the Reynolds number of the downscaled configuration is the same as the original Reynolds number. That's exactly what it says here on this line with these formulas. Let me just try to point that out. Right, so we have here the Reynolds number P is P for problem. This is like our commercial airliner. It has a density that will be the air in which the airliner flies, the velocity of the airliner, the length scale, let's say the wingspan or the length of the fuselage, and the dynamic viscosity of the air. And that Reynolds number should better be the same as the Reynolds number of the model, with density of the fluid in the model, in the wind tunnel, the velocity in the wind tunnel, the length of the scaled object, and the dynamic viscosity of the object. So if we take this equality, these two terms, like the second term and the fourth term, and we say they must be equal, we can regroup the terms and can rewrite this to get a formula for the model velocity, which should be equal to these ratios of density, viscosity, and length times the velocity in the actual problem. Or we can simplify this by using the kinematic viscosity. So we see that the problem velocity, so the velocity of the commercial airliner, is somehow related to the velocity that we need to set in the experiment, and it's related through the ratio of the fluid viscosities. If we use the same fluid, that ratio will be 1, and to the length scale. So let's say if we make the model 10 times smaller, and we use the same fluid, we use air in both cases, well, then we need to go 10 times faster, right? And that's not necessarily easy, right? If a commercial airliner is flying, I don't know, a few hundred meters per second, and you make it 10 times smaller, well, then you have to go already at 10 times, let's say 300 meters per second, or let's say 200 meters per second, so we're at 2,000 meters per second. Well, that's supersonic. And that's, well, first of all, it's difficult to do, it's expensive to do. And third, because then we're going into compressible flows, you will have shocks and everything, the physics will have changed. Okay, so we might fix the Reynolds number, we run into a Mach number problem, which of course also needs to be made. Okay, so this is all not so easy. We need to be careful to well, do something careful about it. But let's say we fix this issue. Let's look at what happens to the forces. So we built our commercial airliner, rescaled it, and we put it in a wind tunnel, and we put it on a scale to measure the forces acting on it, lift force and drag force. Now, these forces, how do they correspond to the real forces in the actual commercial airliner? Well, again, we use Buckingham pi. You remember, hopefully, in one of the first problems that we solved, we showed that the force, I think in the problem we used the drag force, is related to a non-dimensional coefficient. At this point, we call it the drag coefficient. That's just CF, the force coefficient. If we divide the force by density times velocity squared times an area, or here it's just a length scale squared. And that coefficient is just a function of the Reynolds number, okay? Because we made sure in the equation above that the Reynolds number is the same in the model and in the actual problem, we know that through Buckingham pi, this coefficient will be the same. This is already ensured. So we can use this ratio here, or we can say this ratio must be true as well for Fm, the model force, and for Fp. So we can again formulate how the problem force, the force in the actual commercial airliner, is related to the Fm, the force we measure in the model. Okay? So we measure the forces acting on our model in the wind tunnel, and we multiply it by this factor, and we obtain the lift there would be in the actual commercial airliner. That's all pretty straightforward, but well, we have to be careful that we don't scale in a way such that we completely run out of possibilities. We, let's say, become all of a sudden supersonic, or we run into some other problems here. Of course, a Reynolds number is only one story. It's the story if we don't have any inherent timescales, if we're not dealing with gravity forces, if we're not dealing with particles, if we're not dealing with diffusion. For all these effects, there are other non-dimensional numbers, Womersley number, we know, Froude number, Richardson number, Prandtl number, you name it. These are all other numbers that have or have not to be matched depending on the complexity of the problem you want to study. In general, we can say, and this is what it says here, if we want to make the model smaller, that's what you typically want to do with a large aircraft, let's say a car, you want to make it smaller. If we have a smaller model, we usually need higher velocities. That was this formula here. A smaller model usually needs higher velocities because of LP over LM, unless you fiddle with the viscosities. So smaller models need either or higher velocities in the experiment and or smaller kinematic viscosities in the experiment. So how can we do this? Well, let's look at this table down here. Let's look, for instance, at the kinematic viscosity of air at 25 degrees Celsius. And we had a value of 15.5 times 10 to the minus 6 square meter over second, which is 15 times or 15.5 times higher as the viscosity of water, okay? Or it's about, let's say, 3 times higher than the viscosity of air if we cool it down to minus 100 degrees. Okay, so by modifying the fluid, so either cooling down the air or replacing air by water, we come into a lower viscosity range, which allows us to, or compensates a bit for the scale differences and allows us to run the experiment at lower velocities. So in this formula here, the change in viscosity can compensate, at least partially, for the change in scale. And we can play with that. So let's look at one particular example, an aircraft model immersed in water. Okay, so we take a large aircraft, scale it down, and immerse it instead of a wind tunnel in a water tunnel or water tank, as it is usually called. If we compare, or if we look at this formula, and if we compare the kinematic viscosity of air at 25 degrees versus kinematic viscosity of water, we see that we already have a factor of 50.5. So we can downscale our aircraft by a factor of 15.5 and we may maintain the same velocities. Okay? So that's already quite a big help, and that's the reason why a lot of these experiments are done in a water tank. Now, unfortunately, that's not the whole story. There's a few other things we need to consider. What about the power you need to drive this water tank? Right? Just imagine you have a commercial airliner flying at a certain velocity, and you replace, at least virtually, or not virtually, no, in an experiment, you replace this air by water, and you have to drive all the water through, albeit at the same velocity, but it's more mass you have to pump through. So we can compute the power needed to run this model. We can estimate it by the force acting on the model, like the drag force times the velocity. Force times velocity gives us the power in watt. And then we can rewrite the force in terms of the force in the actual problem times the velocity in the problem, which just happens to be exactly the same as the velocity in the model. And that's what we did up here. The velocities are the same, but the forces, of course, are not. And we can evaluate this term here, and we find out that in such a configuration, it's not even the same power we need. We need 3.5 times more power to run the experiment. So even though the airline model is now 15.5 times smaller, it's now in water. So to drive the water at the same velocity, we need 3.5 times more power. And this might actually be a problem to run an experiment at that size. An alternative, and this is where this cold air comes into play. Cold air has the benefit that it's much lighter, right? It's obviously not 1,000 kilograms per cubic meter like water. It's roughly 1 kilogram, or actually 2 kilograms per cubic meter. The difference in viscosity is not as dramatic as the one for water, but still it's a factor of 2.7. So we can already downscale the model by a factor of 2.7 to maintain the velocity. And that's the nice part, we only need about 23% of the power of the original problem. So I just want to show you that there are a lot of factors we can play with, and designing a good experiment, designing a feasible experiment is actually an art. Art to find the right sweet spot where you have a facility where the problem, let's say the wind tunnel or the water tank is big enough to fit your model, where you have enough power to run it, and where, well, for instance, running with cold air is even possible. Another example, a bit smaller scale, not the commercial airline, that's actually something we did in my group some 10 years ago. We wanted to design a model of a semicircular canal. This is the balance sense you have in your inner ear. This semicircular canal is filled with fluid, so it's a flow problem, and it's only about 6 millimeters in diameter. So these loops here have about a size of about 6 millimeters. And we have the problem of accessibility and of size. They're so small, we cannot really look in. And well, obviously they're inside the head, we cannot see them anyway. So we want to build a model which was approximately 5 times larger, so we have accessibility to it. If we wanted to increase by this factor F5, and at the same time, we wanted to maintain the time scale. So we wanted things to happen if something is flowing, we wanted it to move from A to B in the same time. So making it 5 times larger also meant that we wanted to have a 5 times higher velocity. If we then plug it into the Reynolds number, so this is the Reynolds number of the original problem, then the Reynolds number of the model is obviously F times LP and F times VP, so the scaled velocities and the scaled length scale. So we have an F square. That means the viscosity in our model should be F squared times higher than the original viscosity. And that's what it says here. The model viscosity, kinematic viscosity, should be F is 25 times higher than the problem viscosity. By the way, the same story goes if you check for a Womersley number. It also works if you plug in here for LP, you say you have an F times LP, and you see that if you increase the model viscosity by a factor of F squared, the F will cancel out and you obtain the same model Womersley number. Okay, so that's how we found that if we upscaled the model by a factor of 5, we needed to find a fluid to fill this model, which was 25 times more viscous. Turns out that the fluid inside the semicircular canal is it's an endolymph, it's a lymphatic fluid, which has a viscosity just like water, and 25 times higher than water, you find that some hydraulic oils have exactly the right viscosity. So we actually ended up using in this model, let's actually see the model here down. This is the little canal here, about that size, was filled then with a hydraulic oil, just to match the Reynolds number. Okay, so much about dynamical scaling. Now let's move on and let's look at some typical experimental facilities. I have collected here a few photos of some wind tunnel facilities. Two of them you find actually here in Switzerland, and two others are in Germany. Top left, you see the wind tunnel in Emmen, at Ruag in Emmen. It's quite a high quality wind tunnel. And you see two people standing inside the test section. The test section has a width of 7 meters and a height of 5 meters. This is a relatively large test section. Not all wind tunnels have test sections which are that size, and obviously size is also connected to cost. You actually see here a model of an airplane inside this wind tunnel. It's upside down, it's hanging off support, and this support up here is connected to an actual balance, to a scale, which measures the forces, not just the weight force, but also drag forces. Usually it's a multi-component scale, which can also measure torques in different directions, so you get lift and drag forces and also the other components. What this wind tunnel can do, it can reach Reynolds numbers on the order of 10 million. And that's already quite a number for a wind tunnel. Of course, it depends a bit on the models you stick in. If you put in larger models, you can model larger Reynolds numbers. At the same time, if you come too close to the walls, you get boundary condition problems, the wall problems. So the walls, in reality, obviously an airplane is not flying through a channel. An airplane is flying through an atmosphere with nothing around it. So the walls are actually seen as a problem. So there should be enough distance between the model you want to study and the walls of the wind tunnel. Second information here is it reaches Mach numbers up to 0.2. So this clearly is a subsonic wind tunnel, right? There's no ambition to go into anything supersonic. On the top right, you see the wind tunnel we would actually be standing next to or sitting next to if we made this excursion to ETH today. This is the old historic wind tunnel at ETH in the machine lab. It was built in 1934 by Professor Ackeret, who was the founder of the Institute of Fluid Dynamics, or Institute of Aerodynamics at that point. At that time, this was definitely one of the very, very sophisticated wind tunnels. You can also see that its test section, this test section here, it's not quite as large as the one in Ruhr and in Emmen, but it's already quite a sizable wind tunnel. And just for you to understand that, this test section is only the smallest part of the whole wind tunnel. You see here the funnel which collects the incoming air, and there's actually a loop going 1.5 stories down and coming back on the other side. So the whole installation is about 3 stories high. So that's quite a large construction for just a few meters by a few meters of test section. What you see on the bottom left is actually a huge wind tunnel, but it's a different wind tunnel in concept. It's an open wind tunnel, and it's not completely open, still has walls, but it's not really a closed tunnel, right? It's really going into an open space, which has certain advantages for certain problems. I mean, there's no walls in the first place. And BMW is using that, and most other car manufacturers have wind tunnels of that type to actually study their cars in full scale. So there's no downscaling need. One thing I would like to point out here is well, what you see here at the ground, at the floor. This is actually a moving floor. So it's a belt, it's like a conveyor belt, and it can be moved. And why is that? Well, in cars, and especially in, let's say, high performance cars, sports cars, the downforce or whatever is happening between the bottom of the car and the road, so in this little gap between the car and the road, is important to create downforce. For instance, all Formula One teams, for them, it's really, really important what happens in this little gap. Now, if you happen to have just a non-moving solid wall down here and the car sitting on top of it, and you have air passing through, then locally, this will look like a channel with 2 solid walls, and you will develop a Poiseuille flow going in the gap between the car and your floor, right? But that's not really what's happening in reality on the road. But because the road is moving relative to the car, and what will develop in reality is more like a quet flow. Okay? So in order to obtain this quet flow, in order to obtain correct boundary conditions at the bottom of the car, you need to have a ground that is moving at the speed of the car, to get the right boundary conditions. Final example is what we see on the right. It's the European Transonic wind tunnel, which is standing in Cologne at DLR. And what I really want to show you is not actually how it looks inside the wind tunnel, just want to show you the huge size of this building. It's a large building, and of course, there's office space here, but this huge thing is the actual wind tunnel. It's a cryogenic wind tunnel. So it's a wind tunnel, it's one of these wind tunnels where it can really cool down the air. You can cool it down a lot to minus, I think up to minus 150, 170 degrees Celsius to modify the viscosity, just as we looked at it in the examples before. It's a transonic wind tunnel, so you can go up to high Mach numbers, Mach 1.35. So you can not only match Reynolds numbers up to 85 million, which is really large, you can also match correct Mach numbers. So quite a sophisticated system, but you see it's large. This is a costly investment to have such a wind tunnel. If we classify wind tunnels, I mean, there's a lot of little details to classify them, but there's, let's say, at least 3 main ways of classifying a wind tunnel. Let us first look at the wind tunnel on the left. This is maybe the most classical or the most often use large scale, large facility wind tunnel. It's a so-called closed circuit wind tunnel. The test section where we're really running the experiments is again just a small part of the whole object. And the big part is this loop where the air goes around in a loop. On the opposite side, opposite to the test section, we usually have the drive of the wind tunnel with a fan or multiple fans which are driving the flow. At the corners of the wind tunnels, we usually have sophisticated arrangements of vanes, light schaufeln, which are redirecting the flow. It's very important to design these pipes carefully such that whatever arrives here at the inflow to the test section arrives in a, let's say, in a controlled way. People are also talking of silent wind tunnels, and by silent, they're not really talking about the noise, because these wind tunnels actually make a lot of noise. They're actually talking about silent in the sense having little turbulent disturbances. So usually you want to obtain a flow as laminar as possible as it comes in to your test section, such that you have, let's say, a well-defined laminar inflow, and you can study, for instance, transition phenomena, transition to turbulence phenomena. Second closely related design is the closed circuit wind tunnel with open test section. So the only difference really is that the test section itself has no walls. So there's an opening here and air just blows out, and there's an opening here, and at least part of the air comes back in again and goes in circles. By the way, the ETH wind tunnel we have here, you can actually remove this part, these walls, and then you obtain an open test section wind tunnel. The third wind tunnel I'm showing here is the open circuit wind tunnel. Very often these two are confused because this is an open test section but closed circuit, and this really open circuit. So the real difference here is that there's an inflow from the outside and an outflow to the outside, to the ambient air. Now there's no closed loop as what we have here. This is usually a concept of smaller wind tunnels. You see here in the bottom right, a commercial open circuit wind tunnel you can actually buy, and you will see it standing around in several academic research institutions. The test section, I believe this is the little test section. Huh? Okay. So these are really nice smaller wind tunnels where you cannot go well to that large scale as you can go in these big wind tunnels, but they still do a good and nice job. So these were all wind tunnels, and there's a bunch of them around worldwide. You see them mostly in academic facilities, but also car manufacturers have them. Obviously, aircraft manufacturers will have some of them. Very often they're combined with academic institutions and Formula One teams. So most Formula One teams have their own wind tunnels. So it's really fascinating. I once had a chance to go and visit the one at Sauber in Wetzikon and in Hinwil, and it's quite interesting to see what's going on. Now, I also said we can use water tanks. So what you see actually on top right, this is a typical medium scale water tank. And you see here actually the example of a little car, a downscaled little car, which is sitting on a plate, modeling a road. And you see here some streaks. I assume this is probably some dye, some probably fluorescent dye that can be illuminated, and it shines. And it shows nicely here the flow detachment and the generation of turbulent structures at the shear layer. And back here, we have a classical wake recirculation zone, which is fully turbulent. This is a classical water tank experiment. Water tanks can not only be like that, where the model is fully immersed, especially in naval applications. Of course, the interface between water and air is of interest, waves. So these are usually called towing tanks. So just look at the scale here. This is, I call it, I forgot the word in English. It's a ring to save people from drowning. So you just can imagine that the size of this facility. It's really a large-scale facility, and they're dragging or towing a model of a boat, and they can generate waves just to study all the forces here. Right? So it's a two-phase flow, which is actually quite a bit more complex than the one-phase flow as we have it down here. The two other examples are special water tanks, water tunnels. The one on the bottom left is a schematic drawing of a test facility at EPFL in Lausanne. It's a water tunnel for cavitation testing. So they use it in an institute where they study water turbines, and you might know that water turbines in hydropower plants, they have the problem of cavitation. So if the pressure gets too low in a turbine, you get little bubbles, steam bubbles. You have a phase change of the water, and when they collapse again, it creates a lot of force, local force, that might actually destroy the vanes of the turbine. So this is a phenomenon that needs to be studied, and the test section, that's really why I'm showing this, the test section is really, really small. So I once visited that, and the test section was about that big, and the whole loop is again 2 or 3 stories high. You see here a scale 2 meters long, and they actually invested a lot for this bubble trap. So they really wanted to make sure that there's no gas in the air, right? Because they want to study cavitation. They don't want to see air bubbles in the air. Right? It's not the same thing. An air bubble and the cavitation bubble are quite different. So a lot of investment that needs to be done to study in a small test section a very complex physical phenomenon. Final example is something from our lab. It's not very big. It's actually something that fits on a table. Some of you might have seen it already. Some of you will see it if you come next semester to your class on cardiovascular technology. This is a flow loop that we are using in our lab to study heart valve fluid. So it's a flow loop, a closed loop, that is modeling cardiovascular flow just after the heart. It has several sections, each representing an anatomical part. It's like the left ventricle. It has a piston pump, so it's an unsteady loop. Right? It creates this pulsatile flow as we have it coming out of the heart. And these elements here, compliance chamber and this R, which is a resistance, is really modeling the outflow conditions. So compliance is the compliance of the blood vessels. That needs to be modeled to obtain the correct outflow boundary conditions. And the resistance is really the resistance of our microvascular bed, which creates sort of the obstruction against which the heart is pushing with the blood pressure. So even though it's small, it's quite a complex setup to make sure we can model here. Again, this is a small test section. We can study here the flow through heart valves or past heart valves. So this was a little introduction into problems of scaling into a few test facilities. And we're going to continue with actual measurement technologies, mostly velocity measurement, but also pressure measurement. But I think it's a good time now to take a little break here. And we're going to meet again in 15 minutes, and then we're going to continue with the lecture.